Okay, here are some sample problems in kind of mixed up order. Some of them hard, some of them easy, but should give you a complete and full kind of taste of what the test is going to be like. Question 1. An FM radio station is found at 96.1 megahertz, capital M is mega, on the dial, the FM radio dial. How long are the wavelengths it makes? Remember, we've discussed that frequency and wavelength are interrelated. As a matter of fact, the relationship is right there. C is equal to F lambda. Speed of light, speed of an electromagnetic wave, is equal to frequency times wavelength. So we plugged in C, 3 times 10 to the 8th, is equal to the frequency, 96.1 times 10 to the 6, 96.1 mega. So that frequency times wavelength, which we don't know. When you work the math out, you get that the wavelength of the waves is 3.12 meters. And indeed, that is what it is. We know that from FM radio. So that's the simplest one here. Let's look at one a little more complicated. Kind of in the same style, though. An AM radio station operating at a frequency of 950 kilohertz. You'll recall I've said that FM is in the megahertz range. AM is in the kilohertz range. So it's at 950 kilohertz on the radio dial. It radiates 270 kilowatts of power from its antenna. How many photons are emitted by the antenna every second? Okay, the first step, there's several problems in here like this, and this is typical of problems I ask. The first step is we got to figure out, we know it's emitting photons. That's how it's broadcasting its radio station. And because we know the frequency of the photons, we can calculate the energy of the photons. They will all have the same energy. This is the photoelectric formula. It's Einstein gave us this. The energy of the photon is equal to h, which is Planck's constant, times the frequency. So we plug the number in, 6.63 times 10 to the minus 34. That is Planck's constant. 950 kilohertz is 9.5 times 10 to the 5. You can think of it as 950 times 10 to the 3, but I went ahead and kind of cleaned it up. We work it out, and we find out that each photon that is created by this radio station has an energy of 6.3 times 10 to the minus 28. Okay, that's kind of step one. I know how much energy is created by each photon. I now need to figure out how much energy is created by the station in total. Well, it says that it radiates 270 kilowatts worth of power. You'll recall that we defined power as the rate at which you do work, the rate at which energy is converted from one style to another. So the energy that it makes totally, the rate at which it does that, energy total divided by seconds, will give you the total power. The problem told us that it was 270 kilowatts per second. How many photons are emitted by the antenna every second? So that means it's that much power is equal to that much energy divided by 1 second. Well, that's pretty obvious. You just cross multiply with that 1 there, and you get that every second the radio station generates 2.7 times 10 to the 5 joules worth of electricity. Well, all right, that's kind of the second thing we need to learn. Now, the third thing is the total energy generated by the radio station is going to be equal to the energy generated in each photon, or in one photon, times the total number of photons. That's a fairly straightforward statement right there. Total energy of the radio station is the amount of energy in one photon times the number of photons it generates. Number of photons it generates is what it was asking us to figure out. So we plug in total energy here, energy per photon there, number of photons, what we need to know, do a little cross division or cross multiplication. It makes 4.29 times 10 to the 32 photons every second. Strikes me as a lot of photons, but that's a powerful radio station. Let's look at number 3. How many photons per second are emitted by a monochromatic light bulb, which is 650 nanometers long, that emits 75 watts worth of power? I'll read the B part after we've solved the A part. This is a very similar one. Instead of knowing the frequency like we did with the AM radio station, we know the wavelength. But that's okay. This formula here, that's the photoelectric formula. The energy of a photon is equal to h times the frequency of the photon. Now, I went ahead and wrote it this way too. Since the speed of light is equal to the frequency times the wavelength, let me write that here real quick. Since c equals f lambda, I can't get lambda real quick. Lambda, wait. Talk amongst yourselves while I fix this. Since that is true, then that means to isolate for f, I can divide both sides by lambda, so I would get that f, the frequency, is equal to c over lambda. So that's what I did here. I took where I had f, and I replaced it with c over lambda, so you get that the energy of one photon is equal to hc over lambda. Then I plugged everything in here. Here's Planck's constant, there's the speed of light, c, here is the wavelength, let's wait for just a minute there, 650 times 10 to the minus 9, 650 nm. N for nanometers, just like mm is millimeters, lowercase mm is millimeters, cm is centimeters. Well, nm is nanometers, nano is 10 to the minus 9. Now, if any of this here makes you uncomfortable, by all measures, use this formula and calculate. You have the wavelength, 650 nanometers. From that, calculate the frequency, and then stick it in here and calculate the energy of a photon. You'll get the same place. That's mathematically identical, but if the last bit kind of confused you, this bit over here, then by all measures, feel free to not do it. So anyway, when we do the math, we learn that each photon has 3.06 times 10 to the minus 19 joules worth of power, a very small amount. And just like we did in the previous problem, we were told that it is 75 watts worth of power. The power is energy divided by time, so that means 75 watts of power leads to 75 joules worth of energy. Just like we did on the previous problem, the total energy being produced divided by the energy per photon gives me the number of photons, 2.45 times 10 to the 18 photons. That problem is nearly identical to the one on the previous page. Now, B part. If you stand 15 meters from this bulb, how many photons enter each of your eyes per second? Assume your pupil is 5 millimeters in diameter and that the bulb radiates uniformly in all directions. Let me explain that a little bit. When a light bulb turns on, it makes this sphere of light that travels out at the speed of light away from it. So that means that every second, this light bulb makes 2.45 times 10 to the 18 photons. They are obviously very dense close to the light bulb, but as they spread out, the sphere of light gets bigger and bigger and bigger, which means the density of them gets lesser and lesser and lesser. So to figure out how many enter your eye if you're 15 meters away, what we first need to do is figure out the surface area of that sphere. And if we do that, we know that the density of photons will be, that is photons per square meter, will be this number of photons divided by the number of square meters in the sphere. That'll tell us the density of photons. But in addition to that, we know we're asked to figure out about the amount of photons that come in our eyes, and we're told that our eyes are circles with diameter of 5 millimeters. So that said, let's first figure out the area of the sphere 15 meters in diameter. The area of a sphere, you may have to look this up, 4 pi r squared. So it's 4 times pi times 15 meters means the surface area of a sphere of 15 meters in radius is 2,826 square meters. That is, if I take the total number of photons here, 2.45 times 10 to the 18, divide it by that, that gives me, if I want to, that gives me the density of photons per area. However, the area of my pupil, pi r squared, is pi r. Of course, it was 5 millimeters in diameter, so it's 0.25 millimeters in radius. So pi times 0.0025 gives 1.96 times 10 to the minus 5 square meters. I did set the problem up like this because I thought that'd be very straightforward for everyone. The ratio of the area of the sphere to the area of the pupil is the same as the ratio between the photons that are in that sphere and the photons that go in that pupil. So you set up that, and you solve for photons a pupil, and you get that each second one of your eyes takes in 1.7 times 10 to the 10 photons. That is 17 billion photons a second per eyeball for a 75-watt bulb. You have lots of those in your house, which means you take in photons all the time and great heaping piles of them. Okay, let's do number 4. The maximum wavelength of an electromagnetic wave can have and still eject electron from the copper surface is 264 nanometers. What is the work function of the copper surface? All right, you'll recall the little animation I did where we were shining light on a piece of metal, and once the photons got enough energy in them, they were able to start kicking electrons out. That is what this is asking. The expression work function means what is the minimum amount of energy necessary in a given photon so that when that photon interacts with an electron, it can free the electron up. Okay, well, just like we did before, we need to find, we know the wavelength here, 264 nanometers. We need to find the energy associated with that photon, or photon of that wavelength. And yes, I have the energy of a photon is h times f, but just like I did previously, it is also equal to h times c over lambda. That saved me one step. Again, if that gives you any heartburn at all, please don't do it. So here's Planck's constant, there's the speed of light, there is a wavelength, 264 nanometers, 10 to the minus 9. I work all that out, and I figure out that the amount of energy that a photon needs to just barely kick an electron out of a copper atom is 7.53 times 10 to the minus 19 joules. That's a fairly straightforward problem. Let's do one more on this video. Number 5. The threshold frequency of sodium is 4.4 times 10 to the 14 hertz. Let me tell you what that means. That work function, that thing that allows you to kick an electron out, threshold frequency is what is the frequency associated with that work function. Question asks, how much work must be done to free an electron from the surface of a sodium atom? Essentially, it's saying, what is the work function? How much energy do I have to give a photon for it to interact with the electron in such a way that the electron jumps ship and can go somewhere else? Once again, the photoelectric formula, plug in Planck's constant and the frequency that we were given in the problem, bada bing, bada boom, you have that the energy per photon is 2.9 times 10 to the minus 19 joules. That's straightforward. Now, I'll do another video here in a moment and with some more problems, and they'll be just a little tougher. I hope that helped. Thanks.